Hi everyone, this is Facundo Molina. I am a postdoctoral researcher from INDEA Software Institute, and in this talk I'm going to present EvoSpex, a search-based tool for postcondition inference. So postconditions are a particular type of specification whose definition dates back to the work of Hoare, who introduced this notation to analyze program correctness. In this work, a postcondition was defined as an assertion that holds after every legal execution of a given program S. For instance, if we have an implementation of the ABL3 data structure and a routine for inserting elements into the tree, a good postcondition assertion for this method should check that the resulting ABL is a valid ABL, that is, the representation invariant is preserved, that the element that we are trying to insert was effectively inserted into the tree, and that all previous elements in the tree are still there. Unfortunately, these kind of specifications are often unavailable, accompanying the source code, and this situation diminishes the effectiveness of some automated analysis tasks. Thus, having a postcondition inference technique can be useful for a number of reasons. For instance, in the context of regression testing, as implementations evolve with time, one may be interested in checking whether the original behavior is preserved. In differential testing, given different implementations of the same functionality, postconditions can be used to analyze if this implementation behaves the same. In the context of program comprehension, assertions can be used to inspect what the program and their analysis do. Moreover, DICON, a well-known tool for inferring specifications, in particular postconditions, has enabled a number of applications, including program repair and fault localization. DICON is a technique for dynamic detection of likely invariants. It uses dynamic analysis and an ad hoc template-based approach to automatically infer assertions that belong to a standard and extensible assertion language. DICON is a very active and maintained project with more than 20 years of development. It can infer assertions at different program points, such as preconditions, postcondition, and class invariants, but it has limited expressiveness. The assertion language it uses only involves simple arithmetic and logical expressions, and it also has a weak precision. It typically reports false positives and redundant assertions. In order to overcome these limitations, we propose EvoSpex. EvoSpex is a command line tool that, given a Java method and a test suite with executions of such method, allows to infer a postcondition assertion capturing the current method behavior. EvoSpec uses evolutionary computation and a state mutation technique to infer assertions that belong to a JML-like assertion language. EvoSpex allows to perform a guided exploration of a larger search space and incorporate a state mutation analysis that allows to eliminate redundancy and to improve precision. So, given a target Java method and a target test class, the EvoSpec workflow is organized in two phases. First, a state generation phase instruments the test to serialize the pre-post states of every invocation of the target method. Then, the tests are executed to obtain the valid states representing the current method behavior. Invalid states are generated with a state mutation approach representing potentially incorrect behavior of the target method. Second, EvoSpex performs an inference phase, which executes an evolutionary process in order to infer a postcondition assertion. The goal is to infer a postcondition that is satisfied by every valid state and it is not satisfied by every invalid one. To illustrate the usage of EvoSpec, let us consider the following implementation of lists using ABL trees. Also, let's consider as a target method the insertion routine add. This method takes as input an ABL tree representing a list, a position, and an element to insert. Then it updates the tree by inserting the given element in the right position. To infer a postcondition for this method with EvoSpex, we need to perform the two mentioned phases. The state generation phase requires the target method and a test suite with executions of it. As test suites may not be available, one can generate them with tools like a rundup or any other test generation tool. Once received, the invocations to the target method within the suite are instrumented and the test suites are executed. By executing each one of these tests, we build the valid states that are essentially pairs, where the first component is the state before executing the target method, and the second component is the state after executing the target method. Then we use a state mutation technique that, for each one of the valid states, produce an invalid state by mutating the state after the execution of the method. These are random mutations which essentially change the value of some field to a randomly chosen value. Within our artifacts, the states can be generated using the EvoSpex script and using the genStates option, which takes as input a class path, a target test suite, and a target method signature. So for instance, to generate the states for our motivating example, we will provide as parameters the target class path, the fully qualified name of the test suite containing executions of the tree list methods, and the target method, which in our case is the method add, which takes as input an integer and an object. Once we execute the state generation, it first will perform the instrumentation and also the execution of the target test suite. Once it finishes, it will report the number of states generated, and also it will perform the negative state generation involving the mutation process, and also the number of states generated will be reported, as well as the folder in which the states are going to be preserved. After generating the states, we can perform the inference phase. Given the valid and invalid states produced in the previous phase, this phase executes a classic genetic algorithm that evolves a population of candidate postcondition. The algorithm explores the search space of postconditions by using a classical genetic operators such as mutation and crossover until a postcondition is found or some stop criterion is met. To perform the inference phase within our artifact, we can execute the EvoSpex script with the infer option, which takes as input the class path, the target class, in which the target method is located, and a folder containing the states for the target method produced in the previous phase. So for example, to infer postconditions for our case study tree list, we can execute the script as follows, providing the class path, the tree list target class, and the folder containing the states for the add method previously computed. If we execute this script, the evolutionary process will start. At the beginning, the parameters being used for the algorithm are going to be shown, and as the algorithm progresses, it will report the best postcondition assertions found at the moment. And also some information regarding how the mutation operator and the crossover operator were applied is also going to be shown. So when the inference process finishes, it will report the postcondition assertions found. So for our example, it finishes with these postcondition assertions, and for example, it was able to find the assertion stating that the element that we were trying to insert was effectively inserted, that the size value corresponds to the actual number of elements in the tree, and finally that the index in which we were inserting the element is a valid one. So to conclude, EvoSpex is a postcondition inference tool for Java methods. It explores a search space of candidate postconditions through evolutionary computation, and it also supports rich contracts, including navigation and quantification expressions. Finally, EvoSpex is publicly available on GitHub, where you can also find examples and further documentation. Thank you very much for listening.